This example is actually a continuation from example 3. So if you go down in the description below this video, you'll see a link to example 3. So in example 3, we were looking at the same data set as what we have here, which is the overhead width and weight of seals measured from photographs. And in example 3, we did a hypothesis test to show that these two variables are in fact linear, okay, that there was a linear correlation between, and I'll call the overhead width, I'll call this X, and then the weight Y. So there was a correlation between these two variables. In example 3, I typed in the overhead width into my list. I call that list 5, and I typed the weight into L6. And so now if we want to find the regression for this data, and again, the regression equation only makes sense if our data is linear. So before we can do um, question A, all right, get the regression equation and actually start making some predictions using that regression equation, you want to make sure that you first test to see if the data actually is linear, okay? All right, so to get the regression equation, we're going to use LinReg t-test. So below here you can see a screenshot of the calculator. And when you go to LinReg t-test, you want to type in the list where you saved your data. So I put my data into L5 and L6. Make sure to choose not equal to 0 for the alternative hypothesis. And then when we press calculate, you'll see below here the A and B values for that regression line. Okay, so the regression line is y hat equals negative 156.88 plus 40.18x. And again, let's remind ourselves that y hat is the predicted weight, and x here is the overhead width. Okay, and this is measured in centimeters, and this is measured in kilograms. Okay, all right, and before we move on to the next question, let me just write down here LinReg t-test to remind you that that's what test we use to get the regression line. Okay, all right, let's take a look at tab back to the actual data values that we have. So these are the actual data values that we have. And that regression line, that y hat, right, that equation came from this sample data. So if we start making extrapolations for an overhead width of 1.7, notice that the smallest overhead width in our sample is 7.2. So 1.7 is really far away from the rest of the overhead widths in our sample data. So because we're extrapolating so far away from the actual data values, then positive correlation because our R value is 0.9484, which is very close to positive 1. You don't want to extrapolate outside of the scope of your sample data. So the next question says, find the best predicted weight for an overhead width of 1.7 centimeters. So what I have here is a screenshot of the scatter plot that we created of the 6 data values that we have in our sample. And the red line that you see, this red line right here, is the regression line. So that is our regression line, or sometimes that's referred to as the line of best fit. Okay, and that's the equation that we wrote down in part A. So that is y hat is equal to negative 156.88 plus 40.18x. Okay, so if we want to find the best predicted weight for an overhead width of 1.7, so x is 1.7, we want to know what is y hat. Okay, so we can simply substitute x into our regression line to solve for y hat. So let's go ahead and do that. And I just want to remind you that the reason why we can use this equation to predict y hat for when x is 1.7 is because back in example 3, the hypothesis tests for correlation, the conclusion that we made was that the data, right, the two variables did have a linear correlation. Because if it turns out that the variables are not do not have a linear correlation, then you would not want to use the regression line to make predictions. Instead, you would want to use the sample mean. Okay, so you would want to use the sample mean for weights. To make predictions. That would be your best predictor in that situation, okay? But here, when we do this substitution, we get a y hat value of negative 88.57. Okay, so we need to ask ourselves if this makes sense, okay? So getting a negative value uh, means that this can't be correct, okay? So it doesn't seem to make sense. So let's go to question C. Can the prediction be correct? What is wrong with predicting the weight in this case? So in this scenario, let me write this down. The predicted weight is a negative value, okay, which does not seem reasonable, which I should just say, which is not reasonable in this context, okay? Right, so overhead width, so an overhead width of 1.7 centimeters, right, it turns out is well beyond the scope, or you can use the word range, beyond the range of the sample widths, okay? In this situation, any extrapolation that we get, so extrapolation might be off by a considerable amount, and the predicted value may not be valid. Okay, all right. So the takeaway from question B and C is this. You only want to use the regression line. So you only want to use the regression line to make predictions if the data is linear. And we did the hypothesis test in example 3, and we said, yes, the data is linear. However, in this scenario, when we get a value that doesn't make sense for the context of the problem, this is usually an indication that we are trying to predict outside of the scope or outside of the range of the actual data values that we have. So let me, this regression line, okay, this regression line is not going to be the best predictor in that situation, okay? So you have to be careful about extrapolating for values that are beyond the sample data, okay? So even though the hypothesis test supports the claim that there is a strong, and I say strong